So our beginning problem is the following. Find the arc length of y equals e to the x for strange bounds, but usually strange bounds means something nice will happen. A half log 3 up to a half log 15. And then there's a very technical hint. It says, hint, after setting up the length as an integral from something to something of stuff, dx, try the substitution u equals stuff. And like I said, technical, but hopefully somebody was able to decode it. Hopefully lots of people were able to decode that. Do we have an answer? Because we have 5 options. One of them is the right answer. E? E is a good guess. It's not E. Any other guesses? Sorry, what? C? Not C. No, not E, not C. Any other guesses? What? There's no penalty in guessing. B or D? Are you sure you want D? Okay, well, it's not D. And it's not B. Any other guesses? It's A! Great! I was worried no one was going to get it. Okay, good. All right. This is definitely a harder problem. All right. But one of the things that makes it hard is we're trying to do arc length with a simple function. And arc length just does not get along with anybody when it comes to doing out the computations. Now, the good news is we have a formula for it. So we say, okay, we look it up and say we're in the form y equals f of x, which means our length looks like integral a to b square root of 1 plus f prime of x squared dx. And, well, we have our a and b. And the derivative of e to the x is e to the x. If you square that, you get e to the 2x. So we set it up. Now comes the fun part. How do you actually integrate this? Now, you could start by doing some trig substitution. Trig substitution is not the worst thing to try here. But if you do that, you'll eventually still get to the same place. Whereas, just like be aggressive, be aggressive, right? And we're just going to make a crazy substitution, which is all of it. All right, everything is u. And that seems like it might be too aggressive, but let's see where that takes us. So we take the derivative of that, and this is 1 plus e to the 2x to the 1/2, so the 1/2 comes down, 1 plus e to the 2x to the minus 1/2, times the derivative of the inside, 2e to the 2x dx. Well, you can move this term across. The 2's end up canceling, so you get square root of 1 plus e to the 2x over e to the 2x. And you say, aha, square root of 1 plus e to the 2x is u. But how do you get to e to the 2x? Well, if you start with u equals the square root of 1 plus 2, u equals the square root of 1 plus e to the 2x, square both sides and subtract 1. So e to the 2x is u squared minus 1. Which leads us to the following integral. U squared over u squared minus 1. And then the bounds, which were terrible, become nice. And it becomes a partial fractions problem. So it's a partial fractions problem. And we can do some long division, or we can do some sort of fake long division where we add and subtract something. U squared minus 1 over u squared minus 1 gets us to 1. And then we have 1 over this can factor. We do some partial fractions work on the side. We are able to split it. We integrate, we evaluate, and we put it all together. This is not the level of multiple choice problem you're going to see on the exam. Just, I want to assure you, your multiple choice problems are going to be different. But it's good to see fun problems. Any questions on this one? All right. Good. Good. Well, our thought for the day. And came from a scientist, Carl Sagan. This one I have a little bit of history with compared to many of our thoughts for the day. So I had a good friend. His name was Ron Graham, and he was very influential in computer science and shaped a lot of discrete mathematics in the last 50 years. He passed away in July of 2020. The week before he passed away, I flew out and I cleaned out his office. And we were very good friends. And he had a very small bulletin board with like 3 or 4 quotes. And on that was this one. And it says the following: if you know a thing only qualitatively, you know it no more than vaguely. If you know it quantitatively, grasping some numerical measure that distinguishes it from an infinite number of other possibilities, you are beginning to know it deeply. One of the things that often happens, and this is particularly true in mathematics, but I think it happens in other disciplines as well, is we start to think too abstractly too often. Abstraction is a good thing, but only abstraction, only thinking in the theoretical, it sort of separates us from reality, and we don't get to know things well. It's good to actually understand, what are these numbers? What do these things look like? Look at specific examples. Examples are wonderful. And in addition to teaching, I do research, and as most professors do. And I'm somebody who, I love examples. I like to see what's actually happening. So that's the thought for today. Now, why today? Because we're talking about quantitatively. And in other words, getting into the numbers. And so today's topic is actually a very useful thing. When it comes to how you're going to use calculus in the future, the answer is you'll probably have a computer do most of it. It's good to understand how it works. And it's really great for you to be able to do algebra, which is why you're going through this wonderful experience that is calculus. But what is the computer doing? How does it get numbers to do the questions that you're going to ask? In particular, how does it integrate things? So that's what we're going to talk about. So we call this numerical integration. Now, if you look at the history of calculus, and the way that the history of calculus goes is very different from the way you learn it. Because most people will say, oh, well, first came the derivatives, then came antiderivatives, and then you had integration. But it's actually quite backwards. Numerical integration is thousands of years older than the idea of differentiation. They were doing numerical integration ideas back in ancient Greece. And so these are beautiful ideas. And why don't we talk about them more? Well, we do have courses that talk about these things. So if you love working with numerical analysis type questions, you can take these courses. But of course, now with the idea of antiderivatives, we usually think of the way to do integration, find antiderivatives. But there are ways and situations where that's not the right thing to do. Okay, so numerical integration. So we're going to talk about 3 ways. So in other words, we have something we're trying to find the answer for, and we're going to get an approximate answer. We're not going to get an exact answer, but we're going to get an approximate answer. And so our 3 ways, the first way we're going to talk about is Riemann sums. That should sound very familiar because we did that. It's Calc 1. It's one of the first things we learned about integration. Then we're going to get into trapezoid rule. And then we're going to get into Simpson's rule. And you might say, what does all of this mean? Well, essentially it's how we go about finding these numerical values. So delta x, our idea is we're going to take our interval we're working over from A to B and split it up into many pieces. So we'll have n subintervals. We start x0, x1, x2, all the way up to xn. So delta x is going to be the width of the interval. And then these are not subtraction signs, these are dashes. The question is, how much do we weight the points? Now that sounds strange, but we'll explain what we mean. So for Riemann sums, essentially everything gets weighted the same. For trapezoid rule, it's almost the same thing, except the endpoints are weighted a little less, in some sense. And then for Simpson's rule, it's a roller coaster. And that's okay. It all makes sense when we get there. Now, in terms of the formula sheet, we're talking about this little piece here. And it might seem like, wait, how does this fit in? That's for next time. But today, this is where you're going to find what we talk about. All right, so that's what we're going for. Let's begin. So I already mentioned we have our numerical integration. What's our goal? Approximate the total. And we're going to think in terms of area. That just helps us think because calculus is very geometrical. But of course, when we talk about finding totals, even though we phrase in terms of area, it can represent anything. Say, all right, well, what are we going to do? Well, it probably won't surprise you because it's the thing we always do. We're going to break things into small parts. We're going to say, well, what happens in each small part? And then we're going to add it back up again. All right. But now the question about why. Why do we learn this? Why do we need it? Well, there's a couple reasons. One thing that might happen is you might have a curve, but you don't know what the actual function is. And if you don't know what the function is, you can't find the antiderivative. Or you may not even have a curve, you just may have data. Say, well, look, I measured what was happening every second, I got a value. And now I have a set of points. I don't know what's happening in between. I can make some assumptions and say it's probably not going too crazy, but I just have some data. So I definitely don't have a function. But I want to imagine that there were somehow a way to connect the points. And then I want to say, okay, what can I say about totals? Now, another situation which can happen is that we might be faced with an integral where I say, I want to use my fundamental theorem of calculus. So I just have to find an antiderivative. But there might not be a nice antiderivative. We do so many examples where we're able to find antiderivatives, you might start to get the impression, antiderivatives are pretty simple. They're always there. We'll always succeed. No. Antiderivatives are hard to find. And there are many, many cases where it's just hopeless. And even if we can find it, when we get the answer, it might be such a ridiculous expression, it's not very useful. And so in these cases, well, it might be better to say, look, let's just look at the answer numerically. And the last bullet point here is another idea. Maybe we don't really need the exact value. We just need a quick estimate. Estimates can be quick, and for many computations, they suffice. And so it's good to have something that lets you get the job done. So let's start with what we know. Riemann sums, not to be confused with Riemann gardens, different people. Riemann sums. All right, so we're breaking into thin strips. And when we think of Riemann sums, if channel our inner Calc 1 student, we said, we're going to put it in as a bunch of rectangles. So each strip becomes a rectangle. And how do we find it? Well, we know the width, that's the distance downstairs, that's your delta x. Now we have to figure out the height. Well, how do you figure out the height? Well, you use the function. And what we do is we plug in a value somewhere between the left and right points of that little piece and say, okay, whatever the value of the function is there, that's the height. We may plug in the leftmost point. So in that case, the height would be f of x sub k. We may plug in the midpoint, in which case we plug in the midpoint, which is halfway between, that's half of xk plus 1, plug it in, that's our height. Or we may plug in our right endpoint. And then we get our f of xk plus 1. So each rectangle has an area. So if you ignore the sum part, what you're seeing is that's the area in a rectangle, and then you add up each individual rectangle. Now, in terms of what's going on, we're trying to find the total. And so what's going to happen here is we're saying, well, for each interval, we're going to treat it like a rectangle, but think about the top. What we're really saying is treat the function in that interval as if it were constant. So there's this progression that we're going to talk about. So constants. Now you might say, is that realistic? No. Does this work? Yes, but Riemann sums tend to suffer a bit because of our simplicity. It requires you to add a lot of rectangles to get some good precision. All right, so let's go through and do an example really quick. And on a side note, when it comes to numerical, the trapezoid rule and the Simpson's rule, which we're going to talk about next, are the ones you need to worry about. We're not going to test you much on Riemann sums, if at all, but I just want to put that in here for context. All right. So here's an integral, 0 to 2, of 34 over 1 plus x to the fourth dx. On a side note, can we integrate this? What do you think? Do we have the tools? Well, the answer is we could integrate, but it would take us about an hour to do it. I will show you the answer later on. Not the process, but just the final answer. It turns out you can factor 1 plus x to the fourth as 1 plus root 2x plus x squared times 1 minus root 2x plus x squared. Do partial fractions. Then for each part, complete the square, which is a mess. Then you end up with logs terms and arctangent terms and do evaluation. So it is possible, but it would take a long time. So this is a good case of, well, let's see what we get numerically. All right, so when we're doing numerical things, one thing we need to know is how much we're chopping our interval up into. How many strips are involved? So that's our parameter. So here we have n equals 2. So if we think about what's going on, we're going from 0 up to 2. So we're going to cut it into equal sizes, which is 1. So what is delta x? The width of our pieces. 1. Pay attention. Don't forget you need to find this. So delta x equals 1. All right. Now we have our 3 things we need to compute. So let's go through and work those. Let's do our left. So for left, no surprises. We just say what's happening on the left ends. So we can think of this as we have our delta x, our width, and then we have what happens at f of 0 and what happens at f of 1. All right. Well, we can plug these numbers in. What do you get when you plug in 0 into, this is our function. 34 over 1 plus 0, so that's 34. So 1, which is our delta x, 34. And what happens when we plug in 1? 17. Right? 34 divided by 2, 17. And that gives us a total of 51. Okay, great. So there's an estimate. Is it good? We'll find out. But there's other estimates that we can make. All right, so next let's do the midpoint. So midpoint. So that's the halfway point. So what's halfway between 0 and 1? And what's halfway between 1 and 2? Between 0 and 1, halfway is 1/2. And between 1 and 2, 3/2. Okay, so we get 1 times, well, when you plug in a half, you get 34 over 1 plus 1/2 quantity squared, plus 34 over 1 plus 3/2, not squared, to the fourth, excuse me, to the fourth. In the interest of time, you plug that in, and I'll just tell you what it turns out to be. 37.608. All right. Well, that's a very different answer than 51. But that's okay. They're both estimates. Our last one is the right. So delta x. And now the right endpoints for each interval. So the interval between 0 and 1, the right-hand side is 1. Between 1 and 2, the right-hand side is 2. So it'd be the function at 1 plus the function at 2. Now, we've already found the function at 1. That's 17. What happens when we plug in 2? So you'll end up with 34. 2 to the 4th is 16 plus 1 is 17. And 34 over 17 is 2. So 1 times 17 plus 2, which is 19. All right, so there's 3 different estimates: 51, 37.6, and 19. They're not particularly close right now, but that's okay. We'll live with that. So one last comment before we leave Riemann sums is, how are we thinking about it? Well, what we're thinking about it, sort of in my mind, is you have a width, and then for each interval, you have a consistent point, and each interval gets weighted the same. So 1, 1, 1, 1. Or you might say each of your data points get weighted the same. As I said, don't stress too much about Riemann sums. The fun starts on our next one, trapezoid rule. So, let's go to there. Trapezoid rule. Well, same philosophy, break into strips. But now, we're going to do our strips slightly differently. In Riemann sums, we said make it flat on the top. So we're treating it like a constant. For trapezoid rule, we're going to say, no, don't make it flat. Make it a line. And so what we can do is we have our curve of the functions doing something, but we say, okay, we can take the point on the left-hand side, and we can take the point on the right-hand side and connect them by a straight line segment. So that says treat the interval as though the function were behaving like a line. Now that's not unreasonable. One of the things that we sort of often think about, and we say it over and over in Calc 1, is that when you look close, functions look flat. They look like lines. So it's not an unreasonable way to think about going about it. Now, geometrically, the shape that comes out of this is a trapezoid. So trapezoid is we have 2 parallel sides. That's what a trapezoid is. How do you find the area of this situation? Well, what you do, because you have this very convenient thing where you have right angles at the bottom, you say the area is the average of the left and the right-hand side, so that's what this 1/2 h1 plus h2 is. And then that's sort of, in some sense, you can think of it as your average height, and then times it by your width. So For one strip, we have 1/2 the value of the function on the left side plus the value of the function on the right side times the width. So that's our estimate for this one piece. So now how do we get the total area? Well, we add up each piece's contribution. So the area is the sum. 1/2 value on the left plus value on the right, delta x. Now, we're going to rewrite that, and to help us sort of get an intuition about what's going on, is let's imagine a case here where we have several intervals, and we have our x0, x1, x2, x3, x4, x5, and say, all right, so suppose I want to rewrite this, and we'll rearrange. Well, everything has a half and a delta x. Pull that out in the front. So we get this delta x over 2. Now, how many times does x0 show up among these terms? It will only show up once. And it shows up once for the first interval. How many times will x1 show up? Twice, as the right-hand side of the first interval and as the left-hand side of the second interval. So that's why there's a 2. How about for the x2? How many times will that show up? 2. And again, each one of the ones in the middle show up 2 times until we reach the end. How many times does that show up? Once. So that's why you'll see a 1 on the first and the last data points and 2s for all the rest. Because essentially you're stitching together consecutive intervals. So the way I remember it, and this is how it's written down, roughly speaking, in your formula sheet, you have that delta x over 2, and then you're weighing your data 1, 2, 2, 2, 2, 2, 2, 1. So let's try this in practice. Here's this integral, 0 to 2, 34 over 1 plus x to the 4th. Now let's use the trapezoid rule with just 2 strips. Not very many, but that's okay. 0, 1, 2. So we have points. Now we've actually done this computation. We know that f of 0 is 34. We know that f of 1 is 17. And we know that f of 2 is 2. We did that before. That's from our last computation. We don't need to rerun that computation. So when we apply our rule, we still have the same delta x. And when we do this rule, it is important that the intervals are equally spaced. Trapezoid rule and Simpson's rule do not, in their simple form that we have written down, don't follow this pattern if the intervals are not equal. So we say, okay, so we're going to have delta x over 2, and for our case it's very simple. The last point and the first point just have coefficients of 1, and the middle point gets sort of doubly weighted. So it's going to look like that. Delta x over 2, f of 0 plus 2f of 1 plus f of 2. All right. Well, plug it in. 1/2. And we know these values, so it's 34 plus 2 times 34 plus 2. 2 times 17, sorry. Did a computation in my head. All right, 34 plus 2 times 17 plus 2. What does that turn out to be? 35. All right, so here's our approximate answer. Now, there's reasons for us to believe that trapezoid rule should be a better answer because we are better capturing the behavior of the function. It's much more likely it looks like a line than that it looks like a constant. All right, so that's the trapezoid rule, which dates back hundreds of years, unless you work in dentistry, and but that's the story for another day. But, all right. Any questions on the trapezoid rule? Okay. Now the fun one. Simpson's rule. And in some sense, you can kind of see our progression where we're going. We start off by Riemann sums, constant on the top. Then we got the trapezoid, line on the top. You say, okay, what comes after constant, line, parabola? So, Simpson's rule is based off parabolas. So here's the idea. We're going to break it into an even number of strips. It has to be an even number. Because what we're going to do is for each pair of strips, we're going to put them together and say, okay, we have 3 points. So we have this point xk f of xk, this point xk plus 1 f of xk plus 1, and this point xk plus 2 f of xk plus 2. If I have 3 points, there's a unique parabola that runs through those 3 points. And so we find that parabola. Well, we actually don't. We don't need it. We in theory could find it, but in practice we say, okay, what's going to happen? What we're going to do is we're going to say, we'll use the area underneath this parabola as a stand-in for the area under the function. Now what tends to happen is that this says, oh, we're bending. And so we should be doing a better job of matching the function. And this is somewhat true, and we'll get into that in our next class. So we say, okay, well, if we're not explicitly finding the parabola, how does this work? It turns out it's a computation. You can check it. It's one of those computations that most people will only ever do once, and some people not even that often in their lifetimes. But if we know these values, then we can show that the area for the 2 strips is 1/3 times delta x. And then we're going to say, what's the value on the left? 4 times the value on the right, and 1 times the value on, once on the left, 4 in the middle, once on the right. Now, if you sort of run the numbers here, you say, how many points am I adding up? You can think of it as 1 plus 4 plus 1. That's how many pieces of data. That's 6. Divide by 3 makes 2, and you have 2 intervals. So it's at least in the right ballpark. So that's good. All right, so now that's for 1 pair. So what do? We add all the pairs together. So what happens when we do that? So let's see if we can sketch this. Again, a little bit sketchy here. So x0, x1, x2, x3, x4. Okay, that should be good enough. That's an even number of strips. Now, when we look at the first pair, we say, how often does x0 show up? Once. How often about for x1? 4 times, because it shows up. I'm just talking about the first pair. So once on the left, 4 in the middle, once on the right. So that's for that first 3. But then what do? Sorry, first two strips. Then we go to the next 2 strips. And what's going to happen? Well, we're going to get f of x2 again, plus f of x3, plus f of x4. And of course, if we have even more, we keep going. So what's going to happen here is on the very furthest left, we're only going to get 1 contribution. We're only going to have that contribute once. And then we're going to go 4 and then 2, because this is occurring in 2 different pairs. And then 4 and then 2 and so forth and so on. So it's this pattern 1, 4, 2, 4, 2, 4, 2, 4, 2, and then it ends with a 4, 1. So we're weighting the points in this sort of roller coaster fashion. So that's how it works. So that's this sort of shorthand. This is what's on the formula sheet, roughly speaking. Delta x over 3, 1, 4, 2, 4, 1, I think is all it does. But it gets you the idea. It's this 1, 4, 2, 4, 2, 4, 2, 4, 1 as needed. All right. So any questions about this?
Why is it 4? With 4 different?
Why is this 4?
Yeah.
Well, the answer is that's what makes it work.
Okay.
Now, we could sit down and run through the computation, but I don't think it actually helps us. It's just, it works out. It's one of those things like magic. Okay, so let's do this here. Approximate this integral again. And, okay, so again, 0, 1, 2. You have to check, do you have an even number of strips? In our case, yes. It's an even number of strips. Now, note, even number of strips, odd number of data points. So it's not the number of data points, it's the number of strips that needs to be even. And we still have our same facts. F of 0 is 34. F of 1 is 17. F of 2 is 2. So, according to this, delta x equals 1. We'd have delta x over 3, f of 0 plus 4, f of 1 plus f of 2. Well, that's 1/3. 34 plus 4 times 17 plus 2. All right, and 4 times 17 is 68. Good. And then 68 plus 2 makes 70. And so we end up with 104 over 3, I think. Am I doing this right? I think so. All right. And, okay, so what does that give us? I think I may have typed this, done this computation wrong at some point. 104 divided by 3 is? 34.667. Okay. All right. Why do I have a different answer on this page? I feel like I missed a step here. Sorry, what? Well, 4 times 17 is 68, plus 2 is 70, and the plus 34 makes 104. So, strange. Huh. Very curious. Well, you're wondering why I keep saying very curious. It's just like, that's not the answer I was expecting. I have some notes where I've done this before, and I got a different value, so I just want to double check and make sure I haven't done something silly. Because I do several silly things a day. Sometimes they're useful silly things, and sometimes they're not so useful silly things. Oh, no. I'm not going to show you my silliness. I'm not gonna confess to silliness if I don't need to. All right. Well, it's an answer. Okay. I'll have to ponder it. But, yes? No? It's not an answer? Yes, it is an answer. Okay. All right. So, we've been doing this example. Do you want to know what the actual value is? So this integral is 17 over 2 root 2 times 2 pi plus log of 33 plus 20 root 2 over 17 minus 2 arctangent 2 root 2 over 3. I know. You're like, of course it is. 36.384. And yeah. Okay. You probably would say, you know what? I would probably just prefer an estimate. It's going to be more useful. Okay, well, now that we've done that, we still have time left. So there's a problem. Use the trapezoid rule and Simpson's rule with n equals 4 to estimate the integral from 0 to 4 of x to the 4th dx. And in case you don't know your powers of 4, you'll have 0, 1, 16, 81, 256. So, looking at our problem, we have our delta x equals 1. Do we have an answer for the trapezoid rule? 250, 226. Okay, not too bad. Pattern 1, 2, 2, 2, 1, and we add them all up. Okay, how about for Simpson's rule? Do we have a number for that? 205.333333. Okay. And do we have an exact answer? Did anybody have time for that one? 204.8. Now, you'll notice these are not very far off from each other. That's not surprising. And you might say, but you only used just these handful of data points, and yet you were able to get a pretty reasonable estimate. And that's sort of the strength of numerical integration. We'll talk about more of this next time, but that's it for today. Have a good day.